Okay, good morning. This is Dr. Tatterson, and this is Fluid Mechanics, Fluid Mechanics, Chemical Engineering, 330, so to speak. And today we're going to talk about pipe flow. Now, pipe flow is very fundamental, considering how many pipes there are in the world. We should understand different aspects of pipe flow. You're likely, if you're in biomedical engineering, you may die from a pipe flow problem, essentially. And if we look at a pipe, obviously, we're going to assume it's round, no square pipes here. The fundamental variables involved here is first we got, among others, we have the geometry, right? And then we have the diameter of the pipe. And we're particularly interested in the volumetric flow rate going through the pipe and the pressure drop. Those are the fundamental variables of pipe flow. You can also have a situation where you may include roughness of the pipe, maybe, and say a script E sitting here, relative roughness. Our goal is to figure out what's going on here, what's the physics of pipe flow. We got diameter. So the first one, first type of pipe flow problem is a very simple one. Given there's 4 pipe flow problems, by the way, 4 pipe flow problems, typical. Typically, if you're given Q, volumetric flow rate, i.e. the length of the pipe and the diameter of the pipe, you find pressure drop. You find pressure drop. So the second one is given Q, diameter, and pressure drop, you find length. That's another one. Right. And given 3, given diameter, pressure drop, and length, you find flow rate, basically. And for probably the worst or the most difficult problem is given flow rate, pressure drop, and length of the pipe, you find diameter. The fundamental types of pipe flow problems out there. On top of pipe flows, there might be other problems involving finding the horsepower for a pump, perhaps, pump head, or other things like exploring the roughness of the pipe, those sort of things. Now let's go back through here and give these different types of pipe flow problems a name, right? So this one, believe it or not, find pressure drop, you're really performing an energy analysis. It may not seem that to you, but you're doing an energy analysis. Now, the reason why you can say that energy analysis is that basically pressure drop times the volumetric flow rate is basically power, or in a sense, energy per time. That equates to energy per time. Or if you really wanted to call this a little thing energy per time, you could call this, instead of energy analysis, you could call it power analysis. Simply, again, pressure drop times volumetric flow rate is power. You should commit this thing to memory, basically. You should commit that equation to memory. Now this one you're finding length, all right? And so what would you call that? And give it an English name or some sort of verbiage involved. You would probably have to call that equipment placement. Equipment placement. How far apart you can put equipment. An example for that would be, say, the Alaska pipeline, right? Every few miles or so, they'll have a pumping station. And the question is, how far apart should these pumping stations be? And so that would be an example of equipment placement, calculating the conditions of flow. Another example, I had a 1973 Duster, and if you lifted the hood, you'd have the motor. And I swear that motor, basically, of this fairly old car, 1970, had one wire coming out of it, right? I sort of draw it that way. Anyway, so I'll put my fan here. Now when you look under the hood of an automobile, you have situations, very complicated situations. You have air conditioner in there and the ductwork for air conditioning. You have the coolant going through the engine block. You have PVC, whatever. You have all kinds of tubing in there, connecting what and not, trying to prevent pollution, and all that sort of thing. So the car companies, it's a very complicated flow system that's under the hood of your automobile. Lots of stuff going on. Back in the 70s, the automobile was fairly simple. Nowadays, it's quite complicated. So moving right along and given fine Q, and I guess this is flow sizing, basically flow. You have diameter pipe available. You can generate this much pressure drop. Again, you have a pump that will generate the pressure drop. And you have how far apart the equipment is from each other. So you can calculate what sort of flow rates you'd expect to occur. So this would be flow determination, or what? Determination. And the fourth one here would be extremely classical engineering, finding pipe diameter, or essentially this could potentially be called pipe sizing. You're sizing pipe, what diameter do you need to handle the flow rate? So those are the four major pipe flow problems. You might even have a fifth problem. Fifth and sixth problem is as an extension of these. You might want to size a pump. So you have pump sizing. In other words, given Q, pressure drop, length, and diameter that you want, you determine the pump size, how many horsepower, sizing pump. If that would be very important. This one I just sort of stumbled across messing around with this stuff. You want to determine the relative roughness of a pipe. Relative roughness of the pipe. Now, how rough the pipe is. And in a sense, you would be determining the E over D, again, from a volumetric flow rate, pressure drop, length of the pipe, diameter of the pipe, and maybe even the horsepower of the pump. Now, energy analysis up here, to run equipment, you have to sacrifice pressure drop, basically. There's a pressure drop in your body, for example, how much energy your heart is putting in. This is probably the pressure rise across your heart times the volumetric flow rate tells you how much power your heart is using. If we get away from the bio area, just having power analysis, lots of equipment requires you to give up pressure drop. Heat exchangers, for example, is you have to have a certain pressure drop to accomplish the heat transfer. So this is sort of like basic engineering, power analysis, basic engineering, equipment placement, basic engineering, pipe sizing, and they all stem from these types of variables. I think your textbook is okay in this area, but I think they only give you 3 of the 4, but then you should recognize that you potentially can have a couple more sitting there as well. So if we go on and see all these problems start with the mechanical energy balance, which I call MEB, mechanical energy balance, right? If I take a look at the mechanical energy balance, if I write it out, we have the Bernoulli part of the mechanical energy balance, V squared over 2G, and there might be this alpha in here, and then there's a Z. This would be, say, at 0.1, and then you might have a pump involved, so you would have H of the pump. And the mechanical energy balance, in a sense, you can say this is energy in, right, for a piping system. The head that the pump generates, the pressure at 0.1, the velocity at 0.1, and the height at 0.1. And that equals, I'm going to write it expanded up here a bit, P2, pressure at the exit, V2, the alpha in here, over 2G. We'll draw a line in here. And then we have the Z2. And then we have friction. And friction is often written as friction factor length over diameter, velocity squared over 2G. That's one way of writing friction. And then the other way of writing friction would be summation of all the minor loss terms. This is a major loss, major frictional loss. And we have the minor losses due to fittings and elbows and T's. And we can write friction like that. And we can also even write friction as FLE, equivalent length, velocity squared over 2G. And if you write that equivalent length going on. And then for the greenies, the people that are greenies, we can't leave them out. We could potentially have a wind turbine, and a wind turbine takes energy out of the flow. Pump puts energy into the flow. A wind turbine takes energy out of the flow. So we could possibly put the head that the turbine takes out of the flow. Very important. So those are the 4 different pipe flow problems. Very nice. And they all begin with the mechanical energy balance. Let's take the first one up here, unknown pressure drop. So we come to our pumping system, and unknown pressure drop becomes a number. This becomes a number, this becomes a number, this becomes a number, and all this in here becomes numbers. And suddenly P1 and P2, P1 minus P2 would be pressure drop. So what happens, the mechanical energy balance is a direct calculation. So we'll write unknown pressure drop here. And basically, you have, if I take a look again, unknown pressure drop is P1 minus P2. So the mechanical energy balance reduces down to P1 minus P2. And it's a direct calculation, And we'll get into doing one of these a little later. Okay. Just for funsies. Now, unknown length, right? This will be some sort of number. It's the collection of if there's a pump head, velocity head, head, and velocity head, exit, and all these frictional terms involved. There'll be a number sitting here. And you have a direct calculation for unknown pressure drop. Now then, again, we take the pressure drop times the volumetric flow rate, and that will give us the power. That's a very nice equation. Very nice. Now then, for unknown length, right? Again, this would be equipment placement. And we were using two examples, was the Alaska pipeline and also placement of equipment under the hood of a car, right? Or you have two unit operations. Perhaps you have a distillation column. Perhaps you have a mixer that mixes the stuff up. And distillation column might be a reactor, and then after the reactor, there'll be a distillation column. And the calculation of the placement of the reactor versus the distillation column, they got to be placed somewhere. So you'll find if you peruse this equation, the only place length is, unknown length is right here. So what happens is you have length equals, and then you have, after you fill this in, 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 collapse everything down, rearranging some terms, you basically have unknown length. You have some number here in the calculations. So that would be unknown length. And again, we quickly find that this is a direct calculation. Direct calculation. Moving right along here, we find Q, sitting here, volumetric flow rate. So we have this type of thing. Unknown flow rate. Now this is a little bit more trickier here. This is actually unknown velocity / unknown velocity. And again, I start with a mechanical energy balance. What often happens is V1 and V2 cancel out, but you can throw them in to keep it. But unknown velocity, again, sits in the frictional term here. Sits there, sits there, sits there, and velocities are sitting up there. So what happens is, oftentimes, if I collect them all up, I'll have V squared equals some number, right? However, this is not a direct calculation. Not direct calculation. This is a trial and error calculation, because after you collect everything up, usually what will happen is I'll have F and some number sitting there. Excuse me. some F, and it'll be sitting in the denominator here. And what happens, unfortunately, is that F is a function of velocity itself, right? So what happens is the mechanical energy balance reduces down to velocity as a function of some numbers up here divided by F. F is the famous friction factor, right? So we don't know that because we find out the friction factor is a function of, this is friction factor, sorry, let's get up here, sorry. Let me go over that one more time. When I fill in all the numbers on the mechanical energy balance, right, here's the mechanical energy balance up here, what will happen is I'll reduce down to velocity squared over some number divided by friction factor. And what happens, it's not a direct calculation, however, and you have friction factor as a function of, this is friction factor, this is function of velocity. So I have velocity as a function of friction factor, and I have friction factor as a function of velocity. So I have the MEB as being one relationship between friction factor and velocity, and the Moody diagram as the other relationship between friction factor and velocity. Reynolds number, if I draw it up here, moving right on down here. I'll get rid of the MEB here for a second. So, I mean, the mechanical energy, I have this happening to me. I have friction factor as function of velocity, and over here velocity is function of friction factor. And in here, I have the Moody diagram, right? Moody diagram. Where we find friction factor as a function of velocity. The velocity is sitting in the Reynolds number. There's velocity. There's friction factor. So up here we have the laminar regime, we have the transition regime, we have the where friction factor is both a function of E over D and Reynolds number. And up here we have friction factor that's basically independent of Reynolds number. That's very nice for our calculations. When friction, in some cases, this reduces down the friction factor is not a function of velocity. Instead, the friction factor is a function of E over D, which is really great. When this happens to us, it only occurs in this region up here. See, we have the Reynolds number, and we all know that Reynolds number is an extremely important term in fluid mechanics. Unfortunately, or fortunately, and sometimes the Reynolds number doesn't mean anything. It's a flat line here. And we have the relationship where friction factor here is a function of E over D. Up here, this should be probably rewritten as E over D. Friction factor is a function of velocity and E over D. Velocity is hidden in the Reynolds number and the E over D. So we have a trial and error going on where we have the mechanical energy balance and we have the Moody diagram. So there's two. We have two unknowns. Basically, it's a problem. We have two unknowns, which is the Q and the friction factor. Excuse me, velocity and the friction factor. Let's get rid of the Q. Okay, hope that works for you. We'll work some examples of that later. And let's move on to unknown diameter. Now this is the one that's really very difficult. Sometimes it's very difficult. Unknown diameter. Now if we look at the mechanical energy balance again, there is no diameter here, no diameter in the pressure, no diameters there. You got a whole bunch. There's one diameter. And believe it or not, velocity contains a diameter here. Whereas we may know Q, volumetric flow rate, and that is often given to us. We don't have velocity, because velocity is going to be Q divided by area, which is pi d squared over 4 is the area of the pipe. It's a round pipe. So typically, unknown diameter turns out to be really difficult to work. And the mechanical energy balance and for unknown diameter, all right, unknown D, mechanical energy balance for unknown diameter actually reduces down to, if I look here, I'll have F over D to the 5th equals some number here. Okay. And again, this is the MEB and how it generally reduces down to. Okay, and we can some number. And what's interesting about this number, it has units of 1 over length to the 5th power, right? Friction factor has no units. The diameter has 5th power here. And it's length, so we'll have perhaps 1 over meters to the 5th or 1 over feet to the 5th power. So again, we have the relationship between friction factor and diameter. And then we pull out the Moody diagram, which gives you friction factor as a function of diameter. We have our Reynolds number, density, velocity, diameter, kinematic viscosity. Excuse me, not kinematic, absolute viscosity. That also equals velocity, diameter, and kinematic viscosity. So we have friction factor as a function of diameter. And we also have a terrible situation where we have E over D effects. And we have the 4 different flow regimes involved, right? We have the 4 different flow regimes involved. So if we're sitting in here, this is the worst type of problem. We assume an F, find a diameter. Then use the diameter, calculate the velocity, because velocity is not necessarily given to us. We have volumetric flow rate, but we don't have velocity, right? We don't have velocity. So as soon as I calculate the diameter from the mechanical energy balance, I guess an F, calculate a diameter, drop down with the diameter and volumetric flow rate, calculate velocity. With the velocity and the diameter, calculate the Reynolds number. Then I go and put the diameter right here, right, to get the relative roughness. And so I have my Reynolds number, I come up, I follow relative roughness up this way and come across. See, let's go over that real quick because the Moody diagram, when I'm on this line here, these lines over here, I follow a relative roughness effect. These are constant relative roughnesses. So I follow them up, this curve. Then I come up with the Reynolds number that I'm at. So I follow the E over D curve up, hit the Reynolds number, and then I come straight across. Get the friction factor. That's how. And after I do a new calculation, I may have a new Reynolds number, and maybe the new Reynolds number gives me a new relative roughness sitting here, and I come across and get another friction factor. Follow this new relative roughness up. Since the diameter changed, relative roughness changes, and come right straight across. So you iterate, basically, assume a F, calculate friction, or excuse me, assume a friction factor, calculate a diameter. Diameter gives you a new velocity, new Reynolds number, new E over D. You get a new F. You take that new F up here, calculate a new diameter, get a new velocity, come over and get a new Reynolds number, a new E over D, get a new F. Up here, get a new diameter, and so on until you converge. Now, this entire lecture, converge, C-O-N, there's an N in there. This whole lecture is the way you handle real problems. Your book does a really strange, well, there's the do it my way thing here. If you do it my way, you'll get the answer. If you do it the book's way, not so much. Or you will have less of a chance of getting the right answer. See, your book tends to use equations. And you really, really need to use the chart. Because you don't know what the range of Reynolds numbers in here are. You don't know if you're in the laminar, this is the laminar regime. You don't know if you're in the transition regime. You don't know if you're in the regime where the Reynolds number doesn't mean anything. So you're stuck out in the cold, so to speak, if you do it the book's way. My way is the best way, and I would highly recommend you use my way. Now then, if you're sizing a pump, your pump sizing, well, after you've done everything in the mechanical energy balance, so I have this, I have that, fill it all in, and then I calculate HP. So pump sizing, you winds up with HP is equal to some number, and that will be units of height, maybe in feet, maybe in meters. Those are the two common units. And then you can take the pump head, multiply by the volumetric, let's do it this way. Pump sizing, again, let's go back through that. You have the mechanical energy balance. You fill in all the data, and then you calculate HP. You find out HP is equal to certain heights or certain head of the pump. Then you take that head and multiply by the volumetric flow rate and probably throw in a rho G, G sub C, and suddenly you get horsepower. So just for fun, let's do a simple calculation on something and make sure we have our units right, because we all know the units are our friends, correct? So if I look at this, density of water is 62.4 pounds mass per cubic foot, and gravity is 32.2 feet per second squared. The head of the pump, maybe, let's give it 300 feet. And then the volumetric flow rate, let's give it in cubic feet per second. So maybe it's 10 cubic feet per second, which is a lot of flow. And then we divide through, because we have units of mass and units of force and power, right? We got to have G sub C in there to make sure our units cancel. Pounds mass, foot, pounds force, second squared or second. So if I go through, pounds mass cancels pounds mass. Cubic foot cancels cubic foot. This foot cancels that foot. This second squared cancels that second squared. And if I look at that, my units, I'll have this pounds force, right? And I'll have this foot, right? And then I have this second over here left. And I find out that power is also force times velocity. Right, force times velocity, which is also a very nice term to have around. And foot per second, I have about 60 times 300 times 10, or I have 60 times 3,000, so I have 0, 0, 0. Another 0, right? This cancels that, and I'm going to claim this is essentially 60. Again, 60 times 6 times 3 plus the collection of zeros. 1, 2, 3, 4 zeros, and 6 times 3 is 18. Now then I come along and say, well, 550 pounds force feet per second is equal to 1 horsepower. So I'm going to do a quick calculation. This is about 500. So 5, call that 5 into 1800. So what do we got? 300. 360 horsepower. 360 horsepower. So we've sized basically a pump. So, just since pumps are very important, your heart is a pump, we should just quickly talk about pumps a little bit. Basically, you have volumetric flow rate versus head of the pump, right? Pump head. And for a centrifugal pump, it looks something like this. Right. And then you have pump efficiencies. So you have some of the things involved. You don't want to run the pump up in this region. This is a region where basically it's low flow. Low flow. That's not a good location. It's not a good place. And you don't want to run down in this location because you have no pressure, basically. You want to avoid low pressure. So the two extremes here, right there and right there, you want to avoid. And you find out the best efficiency of a pump is floating around in this location, generally speaking. Chapter 14 in your text is an excellent chapter. Go ahead and read it, as well as chapter 8 in your book. You should be reading both of those since we're dashing into pumps. Now, as opposed to centrifugal pumps, there are positive displacement pumps. So positive displacement. This is called pump curve. This thing right here is called a pump curve. So, pump curve. And where do you get pump curves from? Well, you get pump curves from the pump manufacturer, right? That's a sort of a standard test question I ask. Where do you get pumps from? A pump curve from? Pump manufacturers. I mean, they're selling this thing. They should give you what the performance is of it. Now, if you take a look at the mechanical energy balance, the MEB, you quickly find out that the pump head is actually Q squared. So the MEB comes plotting along here. Mechanical energy balance comes plotting here. And where the two intersect is the operating point for the pump. The MEB describes, this is MEB, it's also called the system curve, so it's a piping system. So you have the mechanical energy balance discussing or describing the pump network, or pumping system. And then you have the pump curve, which describes the pump. And where these two intersect on the graph, you have what is called the operating point of the pump. And you biomedical types, there's a certain pressure that the pump puts out, the heart puts out, versus some sort of flow rate the heart puts out. So you come up and come over, and at that location is the pump curve for the heart. So if you're looking for something to do this summer with your smart fellowships or whatever, you develop a pump curve for the heart. I haven't seen one. Oftentimes, engineering is relatively not applied necessarily clearly in the different areas. And if I de-dimensionalize these, right, in other words, this becomes the flow coefficient, this becomes the head coefficient, and then we have a power number sitting in there. Because if we take a look, this is mechanical energy balance, right? We also find, again, if I take this Q and times this H, I figure out how much power is going into my pump or into my heart, right? And the way I would do that is what we just did there. We have the density of blood, gravity, the head that we measured, measurement, pressure, volumetric flow rate. You get an estimate of power. Now, positive displacement pumps, this thing is, these pump curves are very much vertical. Right. So for a positive displacement pump, entirely different design, the pump curve often looks like that, with a slight tilt this way. Now with positive displacement pump, it's dangerous because it just continues on and on and on and on. So you don't want a pipe rupture, and you don't want to have a blood vessel rupture on you. So oftentimes you want to have a relief valve sitting there. So the piping system is you'd have your pump sitting there. Pump exit up here. you would have a pump around loop. You always have some sort of flow rate, and the pressure relief would be up here. That would be your pressure relief. In positive displacement pumps, you don't want this curve to go on and on and on and on and just go up. Instead, you want the pressure. This would be the point of pressure release. So what happens is the flow rate, and then you have some flow coming back and recirculating back through. I'm not quite sure that actually happens in the heart, but it's very helpful. So the pump curve literally is this here. That would be the, and then you have your MEB come along. So your operating points could be changing on you. By the way, as the piping network changes, this is the system curve. As the piping network changes, this operating point will move up and down. Perhaps I have a control valve in the system, maybe a tourniquet, maybe whatever. But this operating point will move up and down along the pump curve. The pump doesn't change, the system curve changes. So you can dial in the different operating points that could be taking place with this pump. In chemical engineering, for example, in filtration processes, the system curve is going to be changing on you. As the filter cake builds up, there's a reduction in filtration. There's a reduction in flow and an increase in pressure drop. So what happens is this one moves up and this one moves to the left. Pressure increases and pressure drop across the filter increases, and there's less flow. So this is kind of intriguing. One of the worst problems that I've ever encountered, ever encountered, was to integrate up a pump curve while determining how much cake was being formed in the filter press. Now, you do one of them there calculations, again, a filter press with the variable pressure drop building up over time, and flow rate being reduced, and the pump head going up. Now, that is one doozy of a calculation, plus the fact that you don't have the data necessary to make sure you can calculate things correctly. Anyway. So, just for fun, this just works some problems here. Just for funsies here, unknown pressure drop. Let's do unknown pressure drop. And remember, pressure drop is P1 minus P2. We have to fill this all in here and to see what happens here. And this is not necessarily an easy calculation. So here's the famous Moody diagram, right? So you should recognize that. You have the laminar regime, which actually has 64 over the Reynolds number. Then you have the transition regime sitting here, which is basically the unknown regime. We run experiments in the 330 lab where we're in this regime. Then you have this line area and this in here, and then you have the fully roughened area where the lines go flat in Reynolds number. Okay. And down here you have this equation, the Colebrook equation. I would not use this equation, right? I wouldn't bother with the equation. The Moody chart is adequate enough. You should also recognize that these data points, well, first off, this is experimental data right here. This is from theory. You can do this from theory. The transition zone actually should go up to about 10,000 or so, I would say. And each one of these flat lines in here is actually really a cloud of points rather than one single line. If you look at the data on this thing, it's absolutely horrid. So anyway, let's do an unknown pressure drop calculation. This make up, say, we have a length of 1,000 feet, okay, and we have a pipe diameter. This will be our length. Yeah, maybe we have a pump in there and say the pump head is 100 feet. But this is how the test questions are made up, by the way. I just pick off some numbers in here. The velocity is probably, say, reasonable velocities are, say, 10 foot a second. 10 foot a second. And there's no height change. In other words, Z1 minus Z2 equals 0. And we ought to hit it with pipe diameter. It's basically straight pipe. Straight pipe. There is no elbows, no T's, no equivalent lengths in here at all. And so if I plot, so this term goes, this term goes, this term goes, Z1, Z2 go, V1 and V2 will go because I have my famous rho VA equals rho VA. 0.1, right? That's 0.2. Densities are the same, areas are the same, velocities are the same. So if the V1 and V2 are effectively cancel each other, Z1 and Z2 cancels each other. So what I have when I eventually put this all together is if I head of the pump now is 100 feet, and in here I'll put in P1 minus P2 times G sub C divided by rho V, or excuse me, rho G. And on the left half side, this is over on the right, this cancels with that, that cancels with that. All I have is friction. Now then, I throw in 1,000 there, and this is 10 squared there, so that's 100. And the diameter I never got around to specifying. So let's just for fun choose diameter, really simple number, 1 foot. So when I clear this thing up, I have my friction factor, right, times 100,000, right, over 2G, right, and then I bring that over minus 100, okay, and then I have, this is 2G, yeah, and I have P1 minus P2 G sub C, and this density rho. Yeah, multiplying through, again, I'll start putting in things in here. I have P1 minus P2, which I'm not going to touch just yet. And I have G sub C, which is going to be 32.2 pounds mass, foot, pounds force, second squared. My density is water, which is 62.4 pounds mass per cubic foot. Gravity is 32.2 foot per second squared. Okay, so that takes care of that side. And this is a foot. So over here I'll have F, and I'll put in here 32.2 foot per second squared. And let's see what happens here. I also have to put in a diameter, right? And my diameter is 1 foot, right? So I have my 1,000 in here. I have my 1 foot sitting there. And very odd unit that looks like it's coming up is foot cancels. I got second squares here floating around, which I don't particularly like. To see what happens over here, I'll have pounds mass canceling pounds mass. I'll have foot canceling foot, second squared canceling second squared there. And so cross multiplying out P1 minus P2, the 32s will go, and I take this to the other side, which would be 62.4. And it looks like this is in the denominator. So I'll guess this is cubic foot, by the way. Cross multiplying, I have cubic foot sitting there, and then I have pounds force. Cross multiplying, it'd be pounds force up here. Pounds force. And if I look at this, I got F 100,000 and divided by 64, roughly. We'll call it 64. And then this is minus 100, I think. And that's 100 foot. I'm having a little difficulty with the units in here. All right, but we'll go back and get that a little later here. What was going to happen is there'll be foot coming out of these calculations. This is foot. And what will happen is the units will come out to be pounds force per square foot, which is the pressure units. All I got to do is worry about this term up in here. This is velocity squared. So I have a foot and foot squared in here. So this 100,000 is actually cubic foot, and that will be per second squared. So I'm correcting my units here. So the second squared cancels second squared. Cubic foot divided by foot squared sitting here gives me a foot. 2 times 32 is about 64. And the units left in this thing will be foot. Okay. So I'm correcting my units. If I multiply through, I get foot pounds force per square foot. Now then, I got this 62.4, and now I have the number part. See, you separate the units out and work the number part. Oh, Dr. Tatterson, why don't I just do this on a computer? And quickly you find that it don't work very well on a computer because you forgot to program it correctly. So, well, anyway, let's go this, and then we have 100,000 sitting here over 64 minus 100. So it looks like we're all set, except for the friction factor. So let's find out what the friction factor is. The friction factor we find out from Moody diagram. And we need to calculate our Reynolds number. If I take a look at my Reynolds number, it's velocity, which will be 10 foot a second, diameter, which will be 1 foot, divided by the kinematic viscosity. Now, the kinematic viscosity of water, this is going to be water, I've got it memorized, 1.4 roughly times 10 to the minus fifth. Okay, foot squared, I think, per second. Okay, the units cancel. So I have basically 1 divided by 1.4. There's a 10 there, and 10 of my times 10 to the sixth power is my Reynolds number, and that should be 1 divided by 1.4. I would claim that that's about 0.7 maybe, just for fun. So I'm looking at a Reynolds number of 700,000. So Reynolds number is 700,000. If I take a look, 700,000, this is a million here. 700,000 is less than that. So I come up here and I'm going to, I didn't tell you about the roughness of the pipe. So we're going to assume a smooth pipe, practically zero. And the zero line for relative roughness is there. And I'm coming up from there, and I can get a friction factor of maybe 0.03. Excuse me, 0.013 would be my friction factor. Right. So if I then clean this mess up, right, if I take 3 of these, I can make this 13. If I take one more, it will be 130, 60, and 130 goes 2 times, right? See, this pipe thing I just picked right out of the blue. I said 200. Just scrap it for a second to see what this turns out to be. Friction factor was 0.013. Okay, and I'm taking 3 of those zeros, making it 13. I'll take another 0, making 130. So this turns out to be roughly 20. And 20, is that correct? Yeah, I'll have 10 left times 2. 64 goes into 130 twice, roughly. So this number is going to be 20. The friction factor has been taken care of. So the number I'm looking at is 20 times 60, or 1,200, right? So I'll have 1,200 PSI, pounds force per square foot. That will be my delta pressure drop. Now, obviously, the pump head was quite excessive, and obviously I would have a very odd, well, maybe not odd, maybe it's actually right on target. The pressure drop, if I put in this 100, I go back and rework the problem, and I have 20 minus 100, that leaves me 80, right? This number is still 20. The whole number here is still 20. Minus 80, or excuse me, 20 minus 100 is 80. Then I have 60 times 80, 0, 0, 6 times 48. That would be negative. That's kind of cool. In one case, I have let's go look at the 2 cases I have. Without the pump, if I do a summary here, without the pump, I don't need this, P1 minus P2 is 1,200 pounds force foot squared. Now then, with the minus 800 and 4,800, I would have the P2 minus the P1 as being, I've reversed these now, and that gets rid of the negative sign, 480 pounds force per square foot squared. Now then, see, without the 100, without the pump, I have a pressure drop of 1,200. With the pump in there, my pressure suddenly goes up because the pump pressurizes. Right? That's kind of cool. It's interesting. Now then, let's get to this into PSI, and we know that 1 square foot divided by 144 is 144 cancels the 120 there, a little bit less. So we're looking about 7 or 8 PSI, right? I'll have, say, 0.8 PSI, maybe 0.85 PSI, times this remaining, it would be 8. So I have 8 PSI or so, pounds per square inch, PSI. And over here, I divide by 144, right, and square foot. So 144 might go into that 3 times. So I have 30 PSI sitting there, roughly. And that's how you do an unknown pressure drop calculation. It's a direct calculation, right? Just as a quick review, we said the length of pipe was 1,000. We put in a pump head of 100. Velocity was 10 foot a second, diameter of the pipe. Rho VA equals rho VA, so the two velocities will cancel. And we find out that we have the pressure drop is equal to some sort of friction factor, which we haven't talked about. L over D, V squared over 2G, and with 100 foot ahead. Plugging in the numbers here, we're going to assume smooth pipe. Make it harder on us or easier on us, depending upon your viewpoint. And we wind up with the pressure drop equaling 120, or excuse me, 1,200 pounds force per cubic foot, or minus, if we put in the pump now, minus 4,800 pounds force per square foot. So there you have it there, unknown pressure drop. Now, let's go ahead and work unknown length. Unknown length. And just for fun, let's go ahead and use this as well. Unknown length. Unknown length, here it was 1,000, excuse me. Here we're going to do unknown length. Here's 1,000. Now then, we're going to assume the same conditions, pump head of 100, and the same Z1 minus Z2, rho VA, velocity is 10, diameter is 1 foot, so we have velocity of 10 and diameter of 1 foot. Now, in this case, the mechanical energy balance, if I take a look at it, somewhere I have it. If I look at my buddy, the mechanical energy balance, I hope I have it. No, I lost it somewhere. Well, anyway, if I take a look at the mechanical energy balance somewhere, I had it. Oh, there we are. Sorry. Now, the unknown length, we got pump head is fine. We have pump head. We're interested in our pressure drop in this case we're going to give you the pressure drop, and we're going to work the situation with the pump. We have a pressure rise of 30 psi, right? Well, and let's just say no pump. Let's just say no pump for a while here. And we're trying to figure out, with no pump, our pressure drop P1 minus P2 was 1,200 pounds force foot squared. Okay, so we're going to work it without the pump. 10 foot a second of diameter is that. Now I go to mechanical energy balance, so that term goes because there's no pump. I have a pressure drop of 1,200, so that's what this is. Velocity of 1 equals the velocity of 2, so those two terms will cancel. Z1 equals Z2, that term cancels. So what we have is the pressure drop, P1 minus P2, G sub C over rho G sitting here. That's going to be equal to our friction factor. Unknown length now, diameter is 1 foot, and the velocity will be 100. We square it, right? So it's foot squared, second squared, divided by 2 times 32.2 foot a second squared. Okay, and if we plug in, this is our pressure drop. Right, just go ahead and make that 1,200 pounds force, pounds force, yeah, it's pounds force. G sub C would be 32.2 pounds mass, foot, pounds force, second squared, divided by density, which is 62.2. pounds mass, foot cubed, and gravity is 32.2 foot second squared. So in a sense that cancels that. Pounds mass cancels that. That foot cancels that. And let's see, what else do we have here? This is per square foot sitting here. So this is second squared. Second squared cancels second squared. And when I clean all this up, pounds force cancels pounds force. When I clean this thing all up, I should get feet. And when I take feet cubed, I multiply top and bottom by feet cubed, and divided by feet squared, the feet cubed cancels feet cubed, feet squared goes into, so I'll have feet coming out of this thing. And 60 goes into 1,200 about 20 times, right? So we got an approximate number of 20. And we got the correct units, because over here, our units are seconds cancel seconds, feet squared cancels that. Okay. So over here we'll have friction factor L 100 divided by 64. Okay. So if we cross multiply, we'll get 1,200. This times that's 1,200 roughly divided by 100, which will give us 12, is our friction factor L. And we go ahead and do the same calculations on our friction factor. Remember, friction factor, if we, again, just for funsies, we pull off our, we assume d over d was 0, and our velocity was 10 times, 10. Reynolds number will be 10 feet per second, foot per second times 1 foot times 1.4 times 10 to the minus 5 feet squared over 3. Yeah. This is our Reynolds number. As you recall, our Reynolds number was 700,000. So if I go to my Moody diagram, the Reynolds number didn't change. I get a friction factor of 0.03. 0.013 is our friction factor. And so I have 20 divided by 0.013 is my length. That would be feet. Or I quickly see that to make this 13, excuse me, wrong direction. That would be, if I do that, I'll just make it just 2, 0, 0. So I have 1.3. That's pretty, that's not what I'm expecting to get. Oh, forgot this little jewel over here. So we'll go, let's try 20 equals 0.013 L 164. There you go. So, right, this is 20, right? Now we're going to go 1200, right, which is that, divided by 100, 1.3. And the units on this thing will be feet. Or I think we could claim that that's close to 1,000 feet. Maybe not quite 1,000, but close. Close enough for government work, as they would say. By the way, government work is not respected much. Anyway, so we worked unknown pressure drop, and we worked unknown length. Believe it or not. So these other problems, we unknown flow rate and unknown diameter. I think we're going to go ahead and work those in class, so to speak. So, anyway, let's flip through Chapter 8 and see what we have going on in Chapter 8. It's very useful to see what happens in Chapter 8. Just tiptoe through here. If I start looking through our textbook, first off, we notice internal flow, and oftentimes I don't know why flow is flow, whether it's internal or external, right? Just between me and you. And some equations down here might be of interest. Again, energy per volume is power per volume. Anyway, let's just move on here. See what else we got. We got flow in ducts and pipes. You're particularly interested in pressure drop and head loss and friction, some circular pipes in here. And we have the famous velocity profile in laminar flow. As a entrance region, okay, you have flow coming in that's flat. Basically, the flow coming in at flat. You have the no slip condition along the walls here, so the flow slows up. And as the flow slows up at the wall, it's got to speed up along the center line. this is a uniform velocity, uniform entrance, but the boundary layers will grow from each side and eventually meet in the middle. And the flow characteristics of this entry region are quite different than the flow conditions in the rest of the pipe. So you take the volumetric flow rate divided by the area, then you have something called the velocity, average velocity in here. And we have our buddy Reynolds number, very important number. I've often pondered whether this is inertial forces over viscous forces. You got density and viscosity. This is a true viscosity, the absolute viscosity, average velocity times the diameter. You can rewrite it in terms of kinematic viscosity, and kinematic viscosity is just viscosity divided by density. Anyway, critical Reynolds number. Critical Reynolds number is the transition between laminar and turbulent flow. So if I take a look at pipe flow, here's pipe flow. On one side I have laminar, on the other side I have turbulent. The critical Reynolds number is floating around. Isn't that cool? A different thing. It probably hurts your eyes. So I'm looking at a critical Reynolds number of maybe 10 to the third up to around 10 to the third, maybe 2,000 up to about 6,000, 7,000, 8,000. It'd be a critical Reynolds number for pipe flow. Anyway, your book says 2,300. When I was growing up, it was 2,100. So, you know, what can I say? Then you should recognize that not all things are circular. Lots of things are rectangular or square or channel flow. So to handle those set of circumstances, the diameter is replaced by the hydraulic diameter. It would be wise if you get your textbook and hold it up as we go through here. And quickly for funsies, you quickly find out for circular pipes, the hydraulic diameter is equal to the diameter of the pipe. What this is 4 times the flow area divided by the wetted perimeter. Right, perimeter. And here you have the Reynolds number. Range is given to you. And as I said earlier, you have vena contracta. In an entry region, you have boundary layers growing from each side. Here's a graphic of that. You have boundary layer growing from that side, boundary layer growing from that side. Deceleration of the fluid at the wall, acceleration forming the famous parabolic velocity profile. In this region, you have very high stresses, you have very high velocity gradients. You have, from a mechanical engineering point of view, you have this as a wear region, right, whenever you're entering. The wear region is simply, you can also have in this region what they call a vena contracta, which is vortices that are rotating this way, and that gives you a high region of turbulence, so to speak, and wear. The heat transfer coefficient is going to be different. The mass transfer coefficient is going to be different. From a biomedical point of view, you may have this. Anyway, so what happens is the entry region is quite different than the rest of the pipe. And to show that, you're particularly interested in the entry lengths, perhaps, and you see that the shear stress at the wall, this tau W, is a lot higher in this region because the velocity gradients are a lot higher. And you have the entry region for a laminar flow, 0.05 Reynolds number. And over here you have turbulent equation for yourself. 10 times the diameter. So you have two major flow regimes. One's laminar flow, and this is laminar flow equations, right? And then you have turbulent flow equations. But anyway, you can go through this if you want, but I'm not going to require you to learn this. It's all a bunch of footwork. The kicker is right down here. This velocity profile, parabolic velocity profile. Very famous velocity profile. Now then, this is not the equations that you should use, okay? You should use the mechanical energy balance, period. This is actually, you'll find that this is, this equation right here is the mechanical energy balance reduced to pipe flow, simple pipe flow. But you should really start with a mechanical energy balance. That way you can't really go wrong. That way the mechanical energy balance forces you to take into account all things that are happening in your process. Now what's happening in pipe flow, okay, is in a sense you have friction happening along the walls, friction along the walls. You have area flow sitting there, friction at the wall. The pressure drop times the cross-sectional area, the pi r squared sitting here, pressure drop that occurs along a pipe times the area of the pipe is equal to the wall friction, tau W is what you're very much interested in, times the surface area of the pipe, which is 2 pi RL. Yeah. So you're very much interested in this tau W. If you're going to die of a heart attack, this is one mechanism. What happens is the friction gets so high in your blood vessels that blood can't get through. Okay. You want to do a little, let's explore that a little bit better. Right. Now then, we spent a lot of time talking about pressure drop, and you find out the pressure drop from the mechanical energy balance, really runs d to the fifth. Okay, that's what the reduction was for the mechanical energy balance. Okay. And what happens is if the diameter gets very, very small, pressure drop gets very, very high. And since the heart is only putting in this much power, and this is limited, right, which then power input limits the available pressure drop that's available, and you find out that you got a very small artery, so to speak, or a blood clot, or a accumulation of plaque inside the blood vessel, and this diameter gets smaller. That means pressure drop goes through the roof by a fifth power. So one day you're walking around lively, and the next day you're dead, because the diameter of your blood vessels around your heart dropped, requiring lots of pressure drop to get the material through, but it isn't happening because your heart can't deliver that much power. Isn't that interesting way of mechanical energy balance causing your death? Yeah. You will likely, not everybody, but one of the major problems with heart failure and one of the major problems with strokes is a lack of blood flow. And the blood flow is due to constriction and the inability for your heart to get the blood into your body. Anyway, so I wouldn't use this equation. I always start with the mechanical energy balance. I don't know where Darcy came from. I don't even know this guy here. It's the Moody diagram. Darcy, I'm sure, was a really great guy. And these are some of the equations, again, I would not use, right? Always start with the mechanical energy balance. Now, I can show that pressure drop is 1 over d to the 5th. That's a possibility as well. Because I got, 1 over d to the 4th. That's what I have up here. Right? So, for laminar flow, you work through the equations, you'll find out that it's actually d to the 4th rather than d to the 5th. Turbulent flow, it's d to the 5th. Laminar flow, it's d to the 4th. Let's see where that came from, just for funsies, because we can't let you not get it correctly, right? So we have this mechanical energy balance. Mechanical energy balance, say my pressure drop, okay, is due to friction only, so I have this FL over D sitting here, this V squared over 2G. Now then, V is Q divided by D squared. 4Q pi D squared. So if I take this and rewrite it in terms of D, right, in terms of diameter sitting here and in terms of Q, I'll have FL over D, then this will be 16 Q squared pi squared D square of square, D to the 4th, and then I have my 2G dangling along. So I quickly find out that pressure drop varies as, well, if I clean this mess up, I'll just have 1 over d to the 5th is what I'm particularly interested in. Pressure drop varies with 1 over d to the 5th. However, in laminar flow, what happens is this friction factor is 64 over the Reynolds number, okay? So, I put in, let's see what we have here. Put in 64 over the Reynolds number. Reynolds number is rho VD squared over viscosity. And then I'll put in this diameter to 5th power here and see what happens. Looks like it's diameter. It's not diameter squared, it's just diameter. It looks like it suddenly becomes diameter to the 6th power. Well, that quite ain't true. Quite ain't true. Because this velocity in here is, again, Q divided by D squared. So if I take it times D, and if I take it times 1 over D to the 5th, right, this velocity becomes Q over D squared, and this diameter is that, and the D squared diameter. So actually what happens in laminar flow, I have it varying as D over 5th. Right. This is wrong, obviously, because so in laminar flow, which is actually beneficial for us, we have 1 over d to the 4th, whereas in turbulent flow it's 1 over d to the 5th pressure drop. So the effect of clotted arteries is reduced somewhat in the fact that the flow is often very laminar-like, as opposed to d to the 5th. This will have less impact. It's probably let people live longer than this would. Anyway, so again, if I go back to this stuff, don't use these equations. They're meant to be informative only. My procedure is general. It's the general way of doing things. Oh, Dr. Tatterson, trial and error is so hard. Dr. Tatterson, this is the modern age. Trial and error you don't have to ever do again. Well, you know what I mean. The old folks actually had quite a bit of it right. Anyway, this is kind of interesting. You rarely see this effect of gravity on flow rate. You got a cosine, you got a sine of the angle involved. This is very nice. Again, the only thing I'm really interested in is the velocity, perhaps, and how the velocity will change with angle. Ah, look at there. Look at there. We got mechanical energy balance sitting there, down there. See a mechanical. Example problem 8.1. Excellent example problem. Gives you some Reynolds numbers to work with. Look at that, 105 meters in head. Look at that fantastic equation. You take a turbine in there, you got a pump in there. That's a very beautiful piece of equation there. Ah, look at that. They talking about pumps here. There you go. Wonderful stuff. Now there you go. Pressure drop and head loss in a pipe. That's a very nice. So we have for McGill out there. McGill is a very nice problem. Worked well, I'm sure. And also over here you have another one. Pressure drop versus head loss in a pipe. That'd be really great. And then we have this continuation of the calculation. Excellent calculations. Here is an example, laminar flow. You have turbulent flow, and here you have instantaneous conditions. See, when the flow exits the pipe, the no-slip condition no longer applies. So the center core slows down and the outer perimeter speeds up. The flow rebalances itself, so to speak. It's kind of intriguing. I don't know if that's important. If you were worried about that, I wouldn't worry about the fact that the flow slows up in the center line and speeds up around the perimeter. Only in the areas of, say, atomization would you worry about this. Anyway, what time we got? We've been at this for quite some time. I suspect that you stopped and started several times already. Anyway, this is page 6363 in your book, in my book at least, where you have this turbulent stuff going on. Turbulent velocity profile. They break up the turbulent velocity profile into what they call the viscous sublayer. The viscous sublayer is not, first, there's not a layer, number one. Number two, it's not viscous. Then they have the inertial sublayer, which is, this is all 1960s stuff. It's so very wrong. Ah, McGill, here you go. McGill, this is sort of like writing an old automobile. Anyway, got some more. It's law of the wall. The biggie is right here. Where's the biggie? I guess your author did not put in the biggie. The one you want to hang your hat on is this right in here. The experimental data sits here, and you have this, and that. Anyway, you have turbulent layer, outer lap layer, whatever that is, buffer layer. This is all the experimental data is here. It's probably an old-fashioned way of looking at it. This is an interesting diagram too as well. See, you have the famous parabolic, the R-squared phenomena for laminar flow. But for turbulent flow, the velocity profile changes with this index n. Now we have the Moody chart and the Colebrook equation. Again, use the chart, right? Use the chart. Do not use this equation. You will get into trouble, right? I don't recommend you use this equation because it doesn't apply in the laminar regime, laminar flow. This is only for turbulent flow, number one. Number two, it doesn't tell you if you're in the transition regime. You're very much interested in the transition regime. Okay. In other words, this is where you want to hang your hat, right? You want to hang your hat. In fact, I wouldn't do any of these in here. You have this equation I wouldn't use. Anyway. Relative roughness, right there. Equivalent roughness. It's good. Table 8.2. Wonderful stuff. Again, Prandtl equation, I wouldn't use that either. The von Neumann equation, I wouldn't use that there anyway. Look at that. Your author has basically the types of flow problems. Well, you notice he has the pressure drop, which is an energy analysis. He has unknown flow rate, which is great, and then he has unknown pipe diameter. These two we will work in class. And unknown pressure drop is here, right? But what's missing is unknown length. What's also missing is pump sizing. So there's a number of things that are missing here. And I see these big X. You got all these nice equations. This is cumbersome, right? My way is nice and clear, got the units canceled. You don't have to program this into your computer. You identify yourself as being very... See, look at that. He works, the author works an unknown head loss problem. Determining duct diameter, look at that. He works a problem for that. Not the way I would work it. And then unknown flow rate in a duct. Not the way I would work it. So, see, again, the Moody diagram is so powerful in the fact that you'll know if you're in the transition regime, whether you'll know if you're in the fully roughened regime, whether you're in a regime where Reynolds number is actually important. So, this is okay, right? Your book is okay, but hardly the end. Okay, minor losses. And I think we're going to stop there. I've been lecturing for, I think, 100 minutes or so. Anyway, quickly, minor losses. You have the loss coefficient, which is this equation right here, and basically it's K times velocity squared over 2G. The units are feet, right? So, or meters. Minor losses, example would be flow through a valve. You have pressure drop there. You have pressure drop maybe due to the flanges sitting there. Okay. You may have pressure drop due to an elbow. right? Or in this case, there's a valve in here. You have a pressure drop due to a valve. You can have pressure drop due to entry region. It matters whether you have a smooth entry or a sharp entry. Doesn't matter very much, I should say. Vena contracta is what I mentioned earlier. And then we have these famous diagrams here. I have re-entrant, whatever. Sharp edge, curved, extended. Anyway. Very famous elbow, 45-degree elbow. Anyway, there's huge books. I shouldn't say huge. There's books that just list these loss coefficients everywhere. And, oh, look at that. We got this here. Look at all the blood vessels and the D over, length over diameter sitting in here. Wow, just look at that. You got it. Actually, says cardiovascular system. There's another system in your body, that lymphatic system, which is basically the materials like water going through your blood, salt water. It's not the blood vessels in the blood, it's the lymph node system as well. And anyway, so you have two fluid mechanic systems in the body, not just one. Isn't it fantastic? Let's see. Do we have a heart showing up here? Anyway, yeah, somewhere in here. Oh, yeah, we also got kidney flow. I wonder what the kidney does, huh? You ever have kidney stones? Anyway, again, I'm going to stop here. Hope you enjoy it. I'm out of town, and we can pick this up after we get into town. In fact, if you're watching this or before the Wednesday lecture, I'm going to finish up Wednesday. I'm going to finish up this coming Wednesday. I'm going to finish up dimensional analysis. Anyway, thank you, and you can this has been videotaped, so you can watch it over and over again. Actually, and hope you enjoyed it. And I'm wide open for questions.